Homework 3 is dividing radicals. So we're going to start with number 1. So there's a handful of different types of examples, and you'll see once you start to simplify them which type it is that you're dealing with. So this one, what you first want to start trying to do is just divide everything. So this one we can divide the 20 divided by 4, which comes out to be 5. And then since these parts are both right under the radical, you can divide them. So underneath the radical, we have 270 divided by 3, and that value comes out to be 90. Make sure, though, you're still writing it underneath the radical. So after you do the division, we end up with this, and then you can take what's left underneath the radical and see what you need to do to simplify it. So 90, you can break down into 9 and 10, and you know that 9 is definitely the biggest perfect square because 10 doesn't have any perfect square factors. So I'm going to take the 90 and break it down into 9 and 10. Then the square root of 9 is 3, and the square root of 10 stays like that. So I multiply the 5 times 3, which gives me 15, and then you leave the 10 underneath the radical. So that is our simplified version for number 1. Next one I want to do is number 7. So this is an example where the division is set up, but 3 isn't divisible by 20, 20 isn't divisible by 3, the way that 270 was divisible by 3. So this one, what you do is you take that property that splits up the numerator and denominator separately, and then we get ourselves in a spot where we need to rationalize the denominator. Okay, so rationalizing the denominator had 2 different types, 2 different methods that you use. One where the denominator was just a monomial, 1 term, and one where the denominator was a binomial, or 2 terms. So here we're in the situation where our denominator is a monomial. The directions in the notes say if that's the case you're in, you multiply numerator and denominator by just that radical that's in the denominator. Okay, so we do this. You'll see as soon as we start to simplify why we end up doing that. Rationalizing the denominator literally means turning the denominator into a number that is rational. Right now, this is a number that is irrational. So multiply these out. Root 3 times root 20, we multiply the values and we get 60. In the denominator, root 20 times root 20, multiply those values and we get 400. And at first glance, it might look like all you did was make it more complicated, but the 400 is one of our perfect squares. So in the denominator, we can simplify the square root of 400 to 20, and now it's a normal, rational whole number. In the numerator, 60, we want to see if there's anything that we can break that down into. 60 is divisible by 4, which is a perfect square. And when you divide out the 4, you're left with 15. So you know that 4 must be the biggest value because 15 can't be broken down any further into perfect squares. So I take the root 60 and I break it down into 4 and 15. The square root of 4 is 2. And then the root 15 is left behind. So one last thing to do here, since these numbers are both out of the square root, you can simplify them down. So the 2 and 20 will reduce down to 1 and 10. So in the numerator, I just have the root 15 and the denominator reduced down to 10. So these are technically the exact same value, but I had to make sure that I didn't have a square root with a fraction or a square root in the denominator. So this is what my answer should look like. All right, we're gonna do one with a binomial. So let's look at 15. So this one, you're still trying to get rid of the radical that's in the denominator, but the method here is we multiply top and bottom by what we call the conjugate of the denominator, and you only do that if you have a binomial like this. So the conjugate is almost the exact same term, except the opposite sign in the middle. So the 4 stays, but then this subtraction will change to addition. So you're going to multiply top and bottom by the conjugate, so it's 4 plus root 3, and you'll do that numerator and denominator. And then once it gets simplified down, just like we did with number 7, you'll see that you will no longer have anything that's irrational left over in the denominator. So numerator, we are going to distribute that 12. So 12 times 4 plus 12 times root 3. So you would just leave it like that. In the denominator, we're going to end up foiling. So 4 times 4 is 16. Outside, 4 times root 3. And then on the inside, negative root 3 times 4, we get this. And then the last, negative root 3 times positive root 3, it's a negative, and then when I multiply the 3's together, I get 9. So just like I mentioned with number 7, at first glance, it really does look like we made this more complicated than it was before. But if you start to look and we combine up our like terms, these ones have like radical parts, so we can combine them. But the positive 4 and the negative 4 would just be 0, so these will cancel out. And then the square root of 9 is just a 3. So when we get a 3, it's a rational number, and we're going to be able to get a nice simple answer. So our numerator is 48 plus 12 times the square root of 3. And then in the denominator, I have 16 from the 4 times 4, and then this ends up being just minus 3. So simplify one last thing, and this denominator ends up being 13. So one thing you would be looking for is if all 3 of these values had a common factor that you could reduce down, but 13 is a prime number, so there is nothing that you can do to reduce that down any further.